Hi, my name is Pedro Antunes. I'm a professor in the Department of Biology at Algoma University, and I have a PhD in soil science from the University of Guelph. This talk is the summary of my review of the scientific literature on ferrochrome production and its potential environmental and health impacts. I'm also including baseline health data for Sault Ste. Marie, potentially linked to its industrial history. This talk is not about being pro or against the ferrochrome facility. It's about searching for scientific information and is my modest contribution so that we as a community can be better prepared to make a decision either pro or against the construction of the smelter at its currently proposed site. In this figure you can see the location of the Ring of Fire. It has enough chromite to meet North America's needs for centuries to come. The problem is that it's in a remote location, very hard to access, so its development depends on the construction of roads or railway, and it also depends on agreement by First Nations. This slide shows a close-up of the Ring of Fire, and it was taken directly from Norond's website, and you can see that Norond holds 85% of all claims in the Ring of Fire district. Here you can see Norond's development strategy for the Ring of Fire. They will start with a nickel-copper deposit, followed by a chromite mine. This is why they need a scalable ferrochrome smelter. The word scalable is important here because once phase 1 of the smelter is built, the facility has much potential to grow. There are several very significant chromite deposits up there, so no doubt that this is an important economic opportunity. So chromium is utilized in industrial applications such as ferrous and non-ferrous alloy and metal fabrication. Ferrochrome is an alloy that contains 45 to 80% of chromium and various amounts of iron, carbon and other elements, and it's used in the production of stainless steel. Stainless steel contains up to 18% chromium. So ferrochrome is produced through a pyrometallurgical process reduction of chromite ore. This is another slide from Norond's website. You can see 2 of their chromite deposits in the Ring of Fire, where they have already measured the amount of available ore and the percentage of chromite in that ore. Large amounts we're talking about, and no doubt high quality material. The company has announced that it can start construction as early as 2025. A potential site was selected, as you can see here on the left-hand side, a location that is west to the Algoma Steel location. And this is why it's important for the community to gather as much knowledge as possible to prepare for public consultations. Here you can see the proposed layout for the smelter. The company is planning to contain and recycle all the waste products on site. This includes slag storage and water treatment. As I mentioned earlier, this is an important economic development opportunity to bring ore from northern Canada and smelt it halfway through for the American market, where several stainless steel plants exist. These plants currently bring in ferrochrome from places like South Africa and Kazakhstan. So it's obvious that having ferrochrome available here in Sault Ste. Marie has the potential to boost stainless steel production in North America, maybe even here in Sault Ste. Marie, where we already produce steel. Why was Sault Ste. Marie selected for the smelter? According to Norond, and I'll cite, the Algoma site is ideal for repurposing an existing site for the establishment of a modern state-of-the-art ferrochrome facility. The proximity to markets and the lower operating costs tip the scales in favor of Sault Ste. Marie. The ferrochrome processing facility is planned to produce high-carbon ferrochrome and employ approximately 1,500 people during construction and between 300 and 500 people full-time. Once Norond has established itself as a high-quality, consistent ferrochrome producer in North American market, we plan to double our ferrochrome production, which would increase employment to more than 500 people. We will develop Black Thor deposit and target European and Asian markets with the increased production. Also, according to Norond, Sault Ste. Marie was selected due to the proximity to suitable electrical infrastructure and the robustness of this infrastructure to support over 300 megawatts of demand, including demand for the electric furnaces, proximity to main rail and natural gas lines, effective road infrastructure and access, cost-effective transportation costs to the location, both from the mine and from the sources of major consumables, especially of anthracite, which is coal that is very important for the smelting process, proximity to markets and low transportation costs to the main ferrochrome customers, availability of trained and experienced workforce to staff the operation, a demonstrated level of community support, the development of the ferrochrome plan leading to the construction being expected to occur over an estimated 7-year period, and they also claim that there is substantial effort to engineer, consult with the community, and complete a very significant environmental assessment required to build the ferrochrome production facility. So why is the community concerned about this? Well, chromium-6 is considered carcinogenic to humans. They're concerned about emissions from the plant, they're concerned about water issues, and they're concerned about waste products containing chromium and other pollutants. It could be in things like dust, slag, sludge, gas emissions. And so in this talk, I will try to go through the ferrochrome process and break it down and look for the evidence. So chromium in the environment is very complex. The speciation chemistry of chromium is complex. I mean, here in this graph on the right, you can see I marked chromium-6 species in red. The formation of this hexavalent chromium depends on pH and redox potential. And in this graph, you can see that chromium-6 forms at high pH, so alkaline conditions, and when more oxidizing agents are present. But even if you have a slightly acidic soil with manganese available, chromium-6 can form. It's complex and dependent on conditions such as pH, nutrients, temperature, etc. And as you know, these vary with in space, and they vary in time as well. Chromium in the environment can come from anthropogenic sources and natural sources. Anthropogenic sources of chromium-6 include chromium ore refining, and these sources contribute about 75,000 tons of chromium, of which approximately 33% are as chromium-6. About 54,000 tons of chromium come from natural sources. Chromium in the atmosphere is removed by rain, and the residence time in the atmosphere is less than 10 days. Chromium-6 in soils can be leached into surface water due to its high solubility and mobility. Chromium-3 is relatively insoluble in water. I included here some guidelines, Canadian guidelines for chromium in drinking water and the environment, but the take-home message here is that they are either 0 or extremely low levels if it's in the environment. Why is chromium-6 carcinogenic, genotoxic? That's because chromium-6 is readily absorbed by a number of different tissues, due to the fact that the chromate anion structurally resembles sulfate, so it can penetrate the cell walls, and once in a cell, the resulting oxidation can release radicals that easily combine with the DNA protein and disrupting our DNA and the DNA of other organisms as well. So the key message is that even at low levels of exposure by inhalation, chromium-6 is a carcinogen and directly interacts with DNA. Now, before I get into the ferrochrome production process, there's some baseline evidence that seems relevant, and this is evidence for Sault Ste. Marie having cancer issues. A recent study published in 2019 in the journal Cancer reported that the national average of acute myeloid leukemia is 30.61 cases per million people per year. Sault Ste. Marie's rate is 44.91, but the P6C area code had a rate of 65.1 per million people per year. So this means that Sault Ste. Marie, along with 4 other industrial cities in Ontario, was flagged as having high rates of cancer. Some local background health data indicated that Algoma had the highest age-standardized incidence rate of cancer in all of Ontario, and the Algoma Public Health Cancer Report for 2015 stated that increased rates of and mortality of lung, bronchus, bladder, kidney, and renal, pelvis, and esophageal cancers in Algoma. This is a photo of the industrial area by the waterfront, taken from Topsail Island in May, and you can see clearly that there is an observation of pollution in the atmosphere. These data on cancer rates are important also from the perspective of the proposed location being suitable or not for industry like this to establish. And another piece of information is that there is evidence for higher rates of certain type of lymphoma within 5 kilometers from industry, things like oil and gas production, chimneys, herbicide crop facilities, metal manufacturing, and plastic manufacturing. This is a satellite view, a satellite map of Sault Ste. Marie. You can see a large brown area to the left there, and a darker area where the Algoma Steel is located, and to the left of that darker area is the proposed location for the ferrochrome smelter. If I overlay on top of that area a map of the dominant winds in the city, you can see that very often we have winds coming from the west into the east end of town, and vice versa as well. The relationship between chromium-6 and cancer is well established. Here we have a study on the effect of hexavalent chromium on the incidence and mortality of human cancers. This is a meta-analysis based on published epidemiological cohort studies. And in the table, in the subgroup analysis of cumulative hexavalent exposure, the higher the concentration of chromium-6 in the air, the higher the risk of cancer death for workers. When the concentration is more than 1 milligram of chromium per meter cube, there is a significant increase in the risk of cancer death. And so as for the time since first exposure to chromium-6, an elevated death risk of cancer was observed, and this is especially true for lung cancer. What is the impact of the ferrochrome production facility on the environment? According to Noront, and I cite, the ferrochrome production facility waste products are primarily greenhouse gases, dust, and slag. Noront will undertake work to evaluate the slag byproducts for appropriate reuse in other commercial applications. Slag products are an inert material and used for construction in many other jurisdictions. The state-of-the-art design of the plant will mitigate and minimize emissions of greenhouse gases and the potential production of dust. The latest cutting-edge facilities in other jurisdictions have no significant emissions. So our main question we have to ask is, do the latest cutting-edge facilities in other jurisdictions have no significant emissions or impacts? Ferrochrome production involves a series of steps, and in a number of these steps, chromium-6 can be produced and potentially released into the environment. These include the transportation, milling, pelletizing, curing, and pellet storage. At a public meeting with Noront, it was clear that the company has a plan that avoids pelletizing and sintering. It is possible that the wet grinding and milling will be done elsewhere. Something to ask. Smelting will be done in DC closed arc furnaces, which generate the smallest amounts of chromium-6 in the industry. Waste products generated during the smelting process mainly consist of slag and bag filter dust generated during the cleaning of off-gas during the wet scrubbing from the closed furnaces. Bag filter dust typically contains the highest concentrations of chromium-6, while the slag forms the largest amount created by volume. The chromium content in slag is between 2 and 12%, present in oxide and metallic forms. Very significant quantities of ferrochrome wastes are generated and discarded in dumps. Given that smelting ferrochrome is a multi-step process, many questions require data to be generated in order to be appropriately answered. First, we need baseline studies to quantify possible natural formation of chromium-6 and identify existing anthropogenic sources. This includes looking at the susceptibility of ore and chromium-containing waste to oxidation. Transportation. What is the likelihood of dust production? I'm going to skip the curing of green pellets, the pelletizing and pellet storage, because that's something the company said already that they are not going to require. Furnace smelting, the off-gas particulate matter from closed furnace with acid operation is reported at 5 micrograms of chromium-6 per gram. Tapping, slag cool down, and product handling. No data is publicly available that quantifies the formation of chromium-6 during tapping. Venturi scrubbing followed by filtering the gas with a sintered plate filter can reduce particulate matters in the off gas to less than 5 milligrams per meter cube. So, question that emerges: how will slag and water from wet scrubbing be stored or treated or recycled? The sludge originating from the wet Venturi scrubber of the off gas should be treated to reduce chromium-6, but then disposed in storage facilities. These are, for example, lined slimes dams. Main et al. And Box et al., and a lot of this information comes from Box et al. 2017, state that leaching is likely. If this happens, there's potential for chromium-3 to come into contact with manganese oxide and oxidize to chromium-6. Box et al. Also state that the possible occurrences of sparingly soluble chromium-6 compounds in ferrochrome wastes are very problematic, and new methods to dissolve both the water-soluble and sparingly water-soluble chromium-6 fractions from such wastes should be a priority for researchers and the ferrochrome producer. So this suggests there are some major knowledge gaps. Box et al. Conclude that the most ideal process will still lead to some chromium-6 being generated, usually in the milligram per kilogram concentration range. Workplace exposure is something that needs to be considered as well. This 2016 study from Tornio in Finland describes workers' exposure to fine and ultrafine particles in the production chain of ferrochromium smelting. They concluded that particle number measurements showed a high amount of ultrafine particles, especially in sintering, alloy smelting and melting, and tapping operations. The workers' personal exposure to inhalable dust averaged 1.40 milligrams per meter cube in the ferrochromium smelter. You can see a micrograph of the metal particles sampled from the smelter, and that chromium is contained in those particles. Now, what can be the fate of waste products in the environment? I found this study from the Tornio plant in Finland, where Scots pine bark was used as a bioindicator for environmental pollution monitoring along two industrial gradients, one of which was around the ferrochrome smelter. Here you can see a map indicating the location of the ferrochrome smelter and stainless steel works, the Kemi mine further away, and the city of Tornio a few kilometers away from the production facility. You can see marked from T1 to T7 the sites where bark samples were collected for analysis. This table contains the test results in the bark for several different metals. You can see in the last row that the background concentration of chromium was 4.3 milligrams per kilogram, and that the average across the T sites, which are those near the ferrochrome and steel production facilities, was 81 times higher at 201 milligrams per kilogram. The ferrochrome and stainless steel factory in Finland, which is considered a state-of-the-art facility, produces detailed reports that are available on their website. This one is taken from their 2018 sustainability report, and it is relevant to read the second paragraph under dust emissions kept at low levels. Our dust filtering systems are extremely efficient and remove 99% of the particles. With the production of 2,913,794 tons of stainless steel, the measured particle emissions from all of our production processes was 388 tons in 2018. The majority of particles were emitted from the ferrochrome production process, with 313 tons with the increased ferrochrome production. In 2017 it had been 193 tons. However, emission measurement results in this process include high uncertainty, causing remarkable fluctuation in results year by year. After presenting these studies, the answer to the question, do the latest cutting-edge facilities in other jurisdictions have no significant emissions or impacts? Well, the literature presented in Tornio reports on emissions suggests otherwise. Another important aspect in this process is who is consulted during the environmental assessment. According to the company, study consultation is expected to involve the following: indigenous communities, the general public, the host municipality, and regulatory agencies. Now, one thing that can be dismissed and that we have to take into consideration is that Ontario has a history of limited enforcement of environmental laws. You can find information about rules on air quality and pollution on the Government of Ontario website, and you can also find much evidence for the lack of appropriate enforcement in this article entitled $30 that was published a couple of years ago in the Toronto Star. In conclusion and some final remarks based on the material presented, since the Sault Ste. Marie ferrochrome production facility will be novel in many ways, it is important to have a prototype vetted through the scientific process to ensure that there will be no risk to people and the environment. At the enforcement level, there should be a zero tolerance enforcement policy and regulations for these types of industries. And if the above is not entirely possible, then we need to consider building the smelter away